Oh, great. It's very fast. We are live now. Thanks, John. Let me record it to the cloud. Okay, let me start sharing this slides. Can everyone see the slides?
Yes, Mohammed, we can see.
Okay, cool. The battery of my headset is very low. I don't know if it will keep working until the end. Let's see. Yeah, I think we are ready. Everyone is here. Okay, good morning, everyone. Good morning to those who are watching us on YouTube. And thank you for joining this another lecture of Mobile Genomics PNS course. Today we will continue talking about other pre-alignment filters that we developed in our research group at ETH Zürich. We will today explain two of these filters, one of them called Magnet, the other one called Shouji. It's a Japanese name, and we will explain why we call it Shouji. All right. So remember that we always upload our lectures before the lecture time, basically on our webpage. So please check the course webpage, and you can access all these slides right now. You can see the videos, the recording, and so on. So during the last lecture in the last week, we explained GateKeeper, which is one of the earliest pre-alignment filters that we developed. And as I explained in the last time, we really need intelligent algorithms and intelligent architecture that can understand the algorithms so that we can handle data well. And we see that genomic data is really overwhelming most of these architectures and algorithms. So we are exceeding the capacity of today's compute infrastructure. And the sequencing machine is still doing really well because they are specialized, customized to do only sequencing. So they don't know how to do analysis or whatever because they don't have the capability to do such kind of computation. So we hope we can get very specialized architecture to do the analysis, similar way as we have specialized architecture for sequencing. And for that, we keep pushing the limit of this compute infrastructure so that we can get the best out of the today compute systems. Okay, this is to recap and to refresh your mind about the problem. We all agree, hopefully by now, that sequence alignment is really computationally expensive. And we need to find a more efficient way that is not expensive. And our goal by that is to accelerate read mapping eventually. We need to reduce the need for dynamic programming algorithms. As we said, dynamic programming is not a bad approach to be used for sequence alignment because it's the only algorithm that can provide optimal solution. But sometimes there are type of sequence or type of genomic sequence pairs that really don't need the dynamic programming to tell us if they are similar or dissimilar, as I will show in the next slide. So we said the main idea of all these pre-alignment filters is that try to distinguish between different types of genomic strings. And we said genomic strings can be similar to each other, and those are basically the things that we are looking for. If they are similar here doesn't mean really exact matching, but rather there are a few differences that may be caused by a disease, or they are actually causing the disease itself, or it could be just sequencing errors. However, whenever there are few errors, then it's more interesting than if we have a large number of errors. And if we have a large number of errors, then we call these genomic sequences as dissimilar strings. They are really different from each other. One of the reasons why they are really dissimilar from each other could be just because they are not coming from the same source, not from the same location, not from the same chromosome, for example. Imagine that you are comparing your DNA to your brother DNA. So most of the time, your DNA should be identical to your brother, except few locations that has some differences that might cause different phenotypes, such as eye color, hair color, and so on. So we are always looking for these few differences to see what caused different phenotype from your brother, for example, or your sister. and your siblings and so on. So the dissimilar strings are normally not interesting and very expensive to compute or to detect, because at the end, we are not going to carry out any computation on them. So we are basically going to ignore them. So once we detect that these genomic sequences are really dissimilar from each other, just ignore them. So whatever computation you apply to these, at the end, you're not going to reuse them. And this is why we call them expensive to detect. If they are similar to each other, then we are interested in more computation on these, such as finding the number of differences, the exact number of differences, the location of these differences, at what sites or at what location they exist, and what type of these differences. They could be insertion, could be deletion, and could be substitutions. So the goal of pre-alignment filtering is to detect the dissimilar sequences using very computationally cheap algorithms. And these normally heuristics, but they don't provide optimal solution because we don't care at this point about optimality, but rather we care about speed and being correct. So we don't want optimality, but we want correctness. What do we mean by correctness? If the number of differences exceed a threshold, then and that agrees with the actual number of differences, then that is correct. But optimality means finding the exact number of differences. We really don't care to find the exact number of differences, but rather we care about knowing whether these differences exceed a threshold or not. Once we figure out this piece of information, then that is a correct pre-alignment filter. Please feel free to ask me questions. I hope my colleagues are watching YouTube, so they can tell me if we got any questions on YouTube from the audience or not. All right, so how this pre-alignment filter works. So I already explained this in the previous lecture, but I want to refresh everyone's mind about it. So the first step is to do indexing, where you have the hash table, where you store some pieces from the reference genome in the hash table, and then you use it to query and try to find potential locations for each read. Once you detect all these locations, you will get subsequences from the reference genome. And then you try to check one by one the similarity between the read and that subsequence extracted at the candidate location in the reference genome. And then you see the similarity between them. So normally we use the pre-alignment filter to detect the similarity between these sequences. And if they are similar, we send it again to the dynamic programming algorithm, which is sequence alignment, or we call it sometimes a verification step. However, there should be some metrics or properties that these filters have. The first one is to filter out most of dissimilar sequences. So as we explained already, that the goal of these filters is to remove the dissimilar sequences so that dynamic programming will operate only on likely similar sequences. The second thing, since we cannot remove all dissimilar sequences, we want to preserve at least all similar sequences. So the similar sequences are the interesting ones. We want to keep all of them. It's okay if we got extra few dissimilar sequences because they are going to be pruned or filtered out by the dynamic programming algorithm anyway. I think I lost the camera. Is that true? Let me see.
Yes, Mohammed.
Okay, let me switch to the laptop camera.
Okay.
You see me now?
Yeah.
Okay, it's a bit worst quality, but I think it works. All right, so these filters should be really quick, really much faster than dynamic programming, because we want to use something cheaper than dynamic programming. Otherwise, there's no point of using a filter that is slower than dynamic programming, because anyway, dynamic programming algorithms is going to check all input candidate locations. Okay, and this is what we are trying to do in this work. We call it Magnet. We published in 2017. And in this work, we try to build on top of GateKeeper. So we try to do accuracy analysis first to understand what caused the accuracy of GateKeeper to be let's say, slightly low compared to existing filters. So first of all, we investigate 4 major sources of false positives in GateKeeper. And we call the first one leading and trailing zeros. These are causing some incorrect detection of dissimilar sequences. The second source, we call it random zeros. The third source, we call it conservative counting. And the fourth source, we call it lack of backtracking. So the first example is here. If you still remember GateKeeper algorithm, when we said you have to generate 3 deletion mask and 3 insertion mask in case your edit distance threshold equal to 3, plus another Hamming mask that is XOR, basically between the 2 sequences. And if you remember how we generate the 1 deletion mask, does any one of you still remember how we calculated? Yeah, feel free to enable your mic and speak up. Does anyone of you remember how we calculate 1 deletion mask over here? So the first one is basically just XOR between the 2 sequences. For the deletion mask or insertion mask, normally we need to operate shift on the query to 1 direction and then do XOR. So do you know how we calculate it exactly? Okay, let me just quickly go over it so you can remember it by now. So 1 deletion mask is basically we shift the query to the right direction by 1 step and then do XOR with the reference. In the 2 deletion mask, we do shift to the query to the right direction again, because still we are deletion mask. So you do shifting to the right direction by 2 steps and then do XOR. The third deletion mask is exactly the same, but we perform 3 steps. Now, when it comes to insertion mask, we perform the shifting to the opposite direction, which is left direction. And we do it gradually by 1 step, 2 steps, and then 3 steps. So when we shift the query by 1 step to the right, there will be a vacant character over there, right? Because when we shift this query, the first character will be second over there. And in the first place here, we will have nothing. So we cannot produce 0 or 1 because there is nothing to compare with, right? So we assume in GateKeeper to be 0. So we have 0 here, then 2 zeros, then 3 zeros. And the insertion mask, we have the zeros at the other direction because we shift this query to the left side. So the last character here will be second last. So we have nothing to compare with. And then we have a 0 over there, 2 zeros over there, and 3 zeros. The rest of zeros over there are just because these characters perfectly match with the other candidate or the reference. But basically, only the first 3 zeros from the last mask are generated by shifting, or vacant characters caused by shifting to the left direction. So these zeros, we call them leading because they are leading over there and they are trailing over there. So these leading and trailing zeros always dominate. Whatever you have in the correct answer, which is highlighted in green, they always dominate. And they cause the ones to disappear from the final result. You can see here in the red highlighted segment, we don't have anyone, although the correct answer include 1 over there. And this is the correct answer coming from dynamic programming approach. So you can compare this with the results we are getting over there. So this is the first source of incorrect detection in GateKeeper. The second source is this example, which we call it random zeros. And hopefully all of you still remember it. If you remember, we tried to change most of the single 0, 2 0 to 1s. So that's why you can see here really a few number of zeros, because most of them being replaced by 1s, especially the single 0 and 2 zeros. However, there are still some random zeros. For example, this guy over there is 3 zeros, right? So we don't replace it, but that is causing a problem still because it's coming right away in front of the 1 over there. So when we do AND operation GateKeeper, that will always dominate. The zeros over there will dominate the 1, and then we will have a 0 in the result. This is also caused to underestimate the number of 1s, which lead to inaccurate detection of dissimilar sequences. The third source, which I didn't explain the last time, I will not go over it right now because it will take a bit of time, but feel free to read the paper to know about conservative counting. But in a brief, when we consider replacing a single zero or two zeros into ones, basically we need to do conservative counting at the end. Why? Because when we replace the single zero or two zeros by one, then we are increasing the number of ones sometimes, especially when there is no zeros in front of this location. For example, here there are three differences, and when we do the AND, there are no zero at all over there. So we don't know if these three ones are coming from the actual differences as we have here, or they are coming from the effect that we did ourselves, which is changing a single zero into one. So imagine if this is really 1, 0, 1, then we are going to change the zero in the middle into one. And when we do AND operation, then we will not get the zero anymore. So in GateKeeper, we consider these three ones to be single one. That is what we call conservative counting. Why we do that? Why we reduce the three into one? Just because we were afraid that these three ones are result of changing a single zero into one. Just to be on safe side, we consider the three consecutive ones as single edit. Okay. So yeah, as I said, please feel free to read Magnet paper. We provide thorough analysis of the accuracy. And the last source of inaccurate results, what we call lack of backtracking. So think about this example. The correct answer, as I said, highlighted in green segments. And when we do AND operation, this is what we will get. So the red highlighted segments is the wrong answer. Why is that? Although it's correct when we do AND operation. So when we do AND operation, these are full segments of zero, and right next to it, full segment of zeros. So when we do the AND, we will get a very long segment of zeros, although we have a difference here. How we know there's a difference? Because simply these zeros do not appear in the same vector. If they appear within the same mask and there is no one between them, then there are basically no edit at all. But since they appear in two different vectors, then there should be a deletion in the middle that caused them to be separated. Why we know it's deletion, not insertion? Because one of the segment appears in the one deletion mask. So the deletion mask will appear only when we have a deletion over there. And once we return back to the Hamming mask, it means there's insertion. If there is a deletion over there, then we'll get the second segment and two deletion masks over there. As long as we keep getting deletions, we will keep iterating over different deletion masks. Once we get insertion, we will do the opposite effect, start going up all the way to Hamming mask. If we get more insertion, then we will shift again to one insertion mask, two insertion mask, three insertion mask, until we lose the track of these because the number of insertions exceed the threshold, which is 3. Please stop me if there's something not clear. So since we don't do any kind of backtracking to these segments where they come from, we don't know whether these are on the same mask or different masks. So we just do AND operation to all these masks, and we got one segment of zeros, and then we calculate the number of ones. So likewise here, when we do AND to all these, so we will get a bunch of zeros over there, but still we don't know if they are coming from insertion or deletion. If a Hamming mask over there contains the zeros, then it means exact match, perfect match because XOR. But once the next segment appears in 3 insertion masks, it means there are 3 inserted characters over there. That's why we got the zeros on the 3 insertion masks. You can see here, probably around there are 3 inserted C's. That's why when we compare them, these 2 segments over this portion, we got the zeros or the exact matches over the 3 insertion masks. So given these insights, we would like to improve the accuracy of GateKeeper. So we know it's really fast, it's really quick since we implemented on FPGAs, But can we do better in terms of accuracy of GateKeeper, since we already know what are the sources of false positives generated by GateKeeper? Okay, so the first one, the first work, we call it magnet. And the key observation we made, correct alignment always include non-overlapping long identical subsequences. What are these? Remember, when we say non-overlapping sequences, they are the green highlighted segments over there. That is always the correct answer, which always long segments of zeros, as you can see over there. It will not be a part of these short zeros, for example. And the key idea is to count the consecutive zeros in each mask and then select the longest segment of these zeros using divide and conquer approach. What does that mean? Let's take an example over there. So we built this set of masks exactly the same way as we did in GateKeeper. However, here, when we use the vacant character for comparison over there, we don't have them as zeros, but rather as ones, or basically nothing over there. But in fact, when we implement them, we have them as one. Why we have them as one? Because they will never contribute to the final results. As we see, the first source of false positive or inaccuracy is basically to have these as zeros. And since we shift the read to the right direction, then will be vacant character over there. And that's why we have them as one here. So to not have any inaccurate results. Okay, so in magnet, the first step is to find the longest segments of consecutive zeros in each mask. So we iterate over each mask one by one. So we start, for example, with this first mask, and we find the segment that has the largest number of zeros. We find this guy over there, highlighted. Then we go to the second mask, and we try to find the other segment in this mask. We find it over there. And the third mask, we find very long one, and then the fourth, the fifth, the sixth, and so on. So we keep doing that all over to each mask. Now we find the longest out of all these found segments. So we collect all of these from each mask. So if we have edit distance threshold equal to 3, then we have 7 masks. Then we have 7 pieces detected from from all masks, and we want to find the one that has the largest length out of all these 7 pieces. We find it to be this one. That's why we have it here as number 1. So this is the largest out of all these longest segments. Now what we do, since we use divide and conquer approach, is to exclude the entire area over there and store this segment in what we call a magnet bet vector. So we have all the zeros extracted from only this segment over there. And then we change everything within this area into ones. Why we change it into ones? Because we want to exclude the entire search area over here from the next iteration. We don't want next time we iterate over the mask to find this again. So we already got it. We already store it in the magnet bit vector. So let's exclude it from there. So we exclude the entire thing over there, and then we add ones surrounding that bit vector we find. So we have 1 over there and 1 over there. Why we add ones? Because this segment is divided basically, or the entire correct answer is divided into segments, and each segment is caused by a number of errors. So when we have this as individual segment separated from the correct answer, that means there should be an edit before it and after it. Otherwise, we will get very long segments of zeros spanning the entire mask. So whenever I have an edit, that's going to divide the correct answer into pieces. And now we solve the first problem, which is the entire thing over there, and we find the answer to be in the middle. So now the time to divide the problem into sub-problems. So what we do is we divide the area to the right side and the area to the left side into sub-problems. So we have a new sub-problems over there and another sub-problem over there. of course, if the answer was panning until the end, then we'll have only one subproblem to the left side. And now we iterate the algorithm, the exact same algorithm. So we will go over each mask in this subproblem, and we try to find the longest segments of zeros. We do the same over there. However, this subproblem is really independent from this subproblem. So we can solve both of them concurrently. And we exclude the area where we find the next longest segment of zeros. We exclude it over there as well, and then we iterate again. So here, there's no subproblem to the right side, so we only extract a new subproblem from the left side over there. That's why we have it as a number 4. And we don't have a subproblem to the left side, but we have a new subproblem to the right side. So we iterate again over 5 and 4, and we try to solve it exactly the same way as we do in the first iteration. Every time we iterate, we store the largest bet we get of zeros in the magnet bet factor. And then we encapsulate it, or we surround that area by ones from the right and left. Here, since it's already reached the first bet, so we don't add 1 over there. Otherwise, it will be longer than the actual sequence length. Here, similar way, we don't add 1 to the right side and so on. So the last step is to count how many ones we got in the magnet bet vector. So this is the magnet bet vector. The number of ones over there will determine the number of edits we detect over there. As you can see, since we call it magnet, it means we attract these sequences. So really, we attract this long segment of zeros, and we store it over there. We attract that, and we store it over there. We attract each of these pieces into the magnet bet vector. How that is helping us to improve the accuracy, as you can see, we never deal with these random zeros. We don't change them. We don't do anything to them, basically. That helps us to detect the correct answer regardless whatever the length of random zeros are. So whether they are single 0, 2 0, 3 0, we really don't care. We just get that over there without having any domination effect caused by these random zeros. I hope the algorithm was clear. I see multiple signs of yes. Okay, that's great. Yeah, so the next step is to implement this, and we choose an FPGA to implement it. But first, until when we should iterate over the problem. So here we iterated 5 times, because as you can see, there are 5 segments of zeros. So we iterate 1, then 2 over the entire thing, then 3 over the 4th, and then we reach the end. And here we iterate another time to the entire subproblem over there, and then we iterate over number 5 alone, and then we reach the end. That is 5 iterations. So how many times we need to iterate normally? Remember that our edit distance threshold is 3. What does edit distance threshold 3 means? So I have this figure for you, the next slide. Here we have 3 errors, right? So this is the exact match between 2 sequences. Imagine we don't have these boxes. These boxes, each of them is edit. Imagine we don't have them. So if we don't have them, we will have very long segment of zeros. So this is full of 0 because we just do XOR between 2 very exact similar sequences. Now, once we have 1 box or 1 edit, it's going to divide the number of zeros into 2 segments. So we have segments of zeros over there, segments of zeros over there, and here single one. Now, if we have 3 boxes, mean 3 edits, it's going to divide the exact match into E plus 1. What is E? Again, it's the edit distance threshold. So we have here 4 segments of zeros, 1, 2, 3, 4. That is going to tell us if your edit distance threshold is E, then you are going to iterate using magnet algorithm only E plus 1 times, because E plus 1 times is enough, really good enough to detect all these 4 segments. If you are iterating E plus 1, but you did not complete solving all subproblems, then it means you have more than E errors, and that is cause to be dissimilar sequences, and then you are really don't need to continue until the end, because anyway, this is waste of time since you already know that these two sequences are dissimilar from each other. Okay, so we choose FPGA to implement it because FPGA really supporting the bitwise operation nicely. And we use this much to build the entire neighborhood map. And this is what we call neighborhood map, is the set of vectors. And as I said, all of them independent of each other. So you can build the entire thing in one shot and concurrently with building all these sets. Okay, now the next step is to check where are these non-overlapping segments or the largest segment of zeros in each mask. And for that, you really need a counter. The counter here is spanning the entire mask or the entire diagonal. So you need to count the number of zeros in each of them. However, you can reset the counter whenever you detect a 1. So you keep counting the number of zeros, assume you find 5 zeros consecutively. And then you store them somewhere. Once you get a 1, you reset that counter and you keep moving through the diagonal or the mask until you find another segment of zeros, and you keep counting it. Maybe you find 7 zeros. So you ignore the first counted one, which was 5, because 7 is larger than 5, and then you consider the 7, you reset the counter, and you move on. So for that, you need a set of counters and the comparators, and then you store the result in what we call magnet bit vector. You do this for each problem. Regardless if it's a subproblem or a problem, for each of them, you need this architecture or this processing element to be operating over each mask. So this is how we implement it. Basically, we have 3 steps. First one, building the set vector, and then counting the longest or the largest set of zeros, and then comparing all of them and pick the largest out of all longest segment of zeros. And we do all of this in parallel for multiple subproblems and multiple sequence pairs. Okay, the key results we got in Magnet is that we improve the CPU implementation of Magnet by at least 74x, especially by using the divide and conquer approach. So if you don't want to use divide and conquer approach, then you will have maybe 7 problems of the same size. Although you exclude the search area for each segment, but still you're operating over an entire set of vectors. But when we do divide and conquer, then each subproblem size getting smaller and smaller as long as we go over the tree of iterations. And in Magnet, we could build up to 2 or 8 filtering units. If you remember, in GateKeeper, we have around 8 or 16 processing units, but here we have 2 or 8. Apparently, each processing element of a magnet is larger than what we have in a GateKeeper, because GateKeeper is just AND operation towards the end. Once you build the vector, you just do AND operation over it, and then you count the number of ones in the GateKeeper bit vector. Here, we do more complex stuff. That's why the footprint of it is real large. You can see it's 10x more FPGA resources than what we have in GateKeeper. However, when it comes to the accuracy, which is very important, regardless the architecture that you are using to accelerate the performance, we see 3.5x to, 4 order of magnitude improvement in accuracy. And that is really huge. Why is that? Because we try to solve all sources of inaccuracy after we do thorough analysis. So we really carefully analyze the accuracy and we find all these sources, and then we try to get rid of most of these sources. However, one of the challenges or the weaknesses of the design we have over there is that we need to, it's really hard to implement on FPGA, because in FPGA, you need to fix most of the parameters. You cannot have, for example, variable length vectors, because the subproblems, we cannot know their size in advance. So once you divide the problem to subproblems, each subproblems has really different size of these vectors. Sometimes they are 10, sometimes they are 20, sometimes they are the entire thing. So we cannot fix these. And we have a lot of workarounds to solve that, but that is taking a lot of resource from the FPGA. The number of lookup table becomes really huge. And this affects the scalability. So we cannot scale with longer sequences or larger edit distance threshold. That was one of the weaknesses we have over there. This is the magnet paper. The source code is available. You can download it, play with it. If you have some ideas, you can change it. And that motivates us to have a better scalable design. As I said, the main problem with magnet was the scalability issue, since we deal with the entire mask as is. So we need to iterate over the entire mask and try to count the number of zeros over there. And what we do, we try to improve it in Shouji. In Shouji, we have a totally different design than what we have in GateKeeper and magnet. And the key observation we made over there, by the way, this work is published in 2019 in Bioinformatics. Yeah, the key observation we made over there is that correct alignment always includes long identical subsequences, which is similar to the observation we made over there. However, processing the entire mapping at once, as in GateKeeper and magnet, is really ineffective for hardware design. So think about if the sequence length is 1 million long, then each of these masks will be 1 million long again, and we will have large number of them. And then iterating over 1 million long sequence is really expensive. So that is for pipelining the design or to do effective, very efficient design over there, it's really challenging to deal with 1 million long sequence and not a single sequence, but rather many of these depending on the edit distance threshold. Remember, the number of these sequences or masks is usually 2e plus 1, where e is the edit distance threshold. The observation we made is based on the dot plot matrix. This dot plot matrix was proposed in 1985, almost 37 years back. And what they do in the dot plot is totally different application than what we have, but we got this observation from these dot plot matrices. And the tool was using this called FASTA or FAST-P. What they do over there is just do pairwise comparison. So T to T, if it is exact match, they add a star or dot. That's why they call it dot plot. And when you have G and G similar to this, we have a star over there. G is similar to G, we add star, 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 and so on. And they build the entire matrix, very simple comparison. And then they are interested in finding a very long diagonal of dots. So you can see here, this is the first diagonal, this is the second diagonal, and why we have them split it, because we have a mismatch in the middle, which is a T and G, for example. We don't have a dot over there, otherwise this diagonal will be full of dots. So in the dot plot, we notice that always these are very long. And since they are long, we really don't need to have a very large counter to go over this, because you can count these two and start next time from here, and then count these two, start next time from here, count these two, and so on. As long as you are still within the same diagonal, then you already know that this diagonal is full of zeros or dots, basically, since you are just moving over the same diagonal again and again. For that, you really don't need a very large counter. What you can do, basically, to count subset of these, and another counter counting here, another counter there, and so on. All of these counters try to count subset of the dots. As long as you are within the same diagonal, then you can accumulate the result later on, concurrently again, and you got the final results at the end. So you really don't need to basically deal with the entire sequence, especially if it is really long, like 1 million long. Then the counter will be 1 million bit long or so, or 2 to the power something. You can use logarithmic to find the number of bits needed for that counter. But it will be huge. It will be really huge. And that not only about the resources, but also about the critical path. So in FPGA design, you should worry about the timing parameters. So what is the time delay in the critical path? And that will determine your maximum frequency that you can go up to. And that will determine the speed of the design, basically. Okay, I hope it's clear. Let me delete the annotation. Yeah, please feel free to stop me if you have any question, any doubt. All right, so the key idea we made to use overlapping sliding window approach to quickly and accurately find all long segments of consecutive zeros. So we use this equation similar to dot plot, where if a character equal to a character, in the corresponding character, we have in the matrix 0, otherwise we have 1. And this is the description of how we build the matrix. But anyway, I have an example, maybe better than the theory we made. So first, we build what we call neighborhood map. This is the neighborhood map. We build not as we do in Magneton GateKeeper. We don't care about making all these diagonals equal length. They are, in fact, not equal length. As you can see, the main diagonal is the longest segments over there, and everything else is less than what we have over there. And we build only 2e plus 1, similar to what we have in Magneton GateKeeper. So 2e plus 1 of these diagonals, starting from the main diagonal and e other diagonals to the right and e other diagonals to the left. And how we build it, just compare G to G, we find 0, G to G, 0, and so on. You continue over there. Now, next step, we have a search window that is of size 4 cells diagonally. So in the diagonal direction, we pick 4 of these cells all over the diagonals, regardless the length of each diagonal. So here 4, 4, 4, and so on. Of course, towards the end over there, we won't have 4 because these are shorter than the other diagonals. And what we do is basically to count diagonally how many zeros we have over there. So we have here single 0, single 0, single 0, here 4 zeros, single 0, 2 zeros, and a single 0. And we pick the one that has the largest number of zeros because we believe this segment of zeros is part of the solution, but we don't know. It could be after this search window because we are blind at this stage. We cannot see anything else because each search window will build its own data inside. So the entire thing in the middle will be built by this search window. But we don't build the entire thing over there as we do in Magnet or GateKeeper. And we don't know if the rest of the diagonal will be full of zeros or not. But we believe, since these sequences of long zeros or of consecutive zeros are normally long, so we believe that this sequence is part of the correct answer. Our assumption lead to correctness, but not optimality, of course, because we always underestimate the number of ones. However, we never overestimate. So we never assume that these are edits, for example. We always try to find the zeros, and we assume they are part of the answer solution. Now we pick the one that has the largest number of zeros, and we store it somewhere. We call it a Shouji bit vector. And then we proceed with the next search window. That is the next 4 cells. And we keep repeating the same thing. So every 4 cells diagonally will be calculated by different search window. So we got the next one. However, because this search window is really overlapping with the previous search window, so let me change the color over there. If you still remember, we have, let me find a rectangle shape. We have this as search window 1, and this was search window 2. Now, when we want to store the results, we will have 4 bits from this guy and another 4 bits from the other guy. Let me maybe change the colors. Let's use green. So we have 4 coming from this and 4 coming from that. What are these 4? These are the bit vector within this search window that has the largest number of zeros. For example, here we got 3 zeros and 1. So we got here 3 zeros and 1. And here we got 4 zeros, right? Now, we want to store them in the Shouji bit vector. You can see they contradict each other, or there's a conflict. Which one to store? This guy over here or this guy over there? So the good thing that as we progress, we always store one bit, which is the first one. So this bit never overlap with anything else because we shift the second search window by one step. As you can see, it does not span this column again. So that is a good thing because the bit resulted from the first column will be stored as is. Nobody will affect it. Now the problem with the next three bits over there, because they are overlapping with the next search window, so which one to keep, which one to remove or to replace. Our heuristic says, whatever maximize the number of zeros, take it. Otherwise, ignore. So if the new set over there, increasing the number of zeros stored here, take it. Otherwise, just ignore. So let's see what will happen. Apparently here, all of them zeros. So we remain the same zeros, regardless if we take it from the new set or the old set. Still, the first three bits over there zeros. The last three bits over there are zeros. So that's why we don't have problem. But later on, we might have a problem from the other bit vector. Maybe I didn't continue the search windows, but you can infer it yourself. But the rule is whatever maximize the number of zeros, take it. So if we have here all ones, ignore this set and take the previous one. And just keep continue doing the same thing you are doing over all search windows. Now, as you can see, the sub-problem size become much smaller than what we have over there. At most will be 4 by 2e plus 1. So we fix the number of columns always to 4. And the number of rows depends on the edit distance threshold, but at maximum, or it will be basically 2e plus 1. So 2e plus 1 times 4, that is the size of each subproblem. As you can see, it's really very much smaller than what we have in GateKeeper, Magnet, and so on. And then the last step is to count how many ones we have within the bit vector. Please let me know if I should explain it again. How is it? Good? Okay, I see multiple signs of yes. All right, so let's continue. Now, why we call it Shouji? So I have a video from a friend in Japan. He was working with us at Safari, and he sent me this. So let's watch it together. So that is the door he has in his grandmother in Japan. So the door, as you can see, is slide to open, or basically is this shape. So that is exactly what we are doing in Shouji, right? We are sliding the search window over 4 columns, and every time we keep looking within this search area, the new search area, finding the largest number of zeros. So that's why we call it Shouji. Let me move on. Okay, now maybe someone wonder why we have it as 4 bits or 4 columns. Why each search problem has the width of 4? Why not 5? Why not 6, right? Because 4 is still small, right? You can increase it to 10. It won't be a problem with the FPGA resource. So we did a theoretical analysis before we picked that number, and let's see the effect of different window sizes. So before I go into the plot, I want to tell you that the minimal possible length of identical subsequence is single match. So if you have a sequence and another sequence, the minimum number of matches to have is single zero, right? Of course, you can have a mismatch, but that is not interesting since we are always looking for zeros in Shouji, not in ones. The smallest number of zeros we can have is 1 0, right? And to have 1 0, we need to be surrounded by ones. Otherwise, it will not be single zero. So we need to have 1. Where's the cursor? 1, 0, and then 1. This is how we call it single zero. Otherwise, if it is 1, 0 something, then 0, 0, that is not single zero, right? So let's agree, all of us, that we need at least 3 bits for the reason I mentioned. I cannot see the cursor. Yes, over here. So let's assume that the minimum number of bits we need is 3 bits. That's for sure. Just to have it 101, that is the smallest number of matches. Now let me clear. Yeah, whenever I use a notation, I lose the cursor, so I cannot see it. Yeah, trying just to guess where's the cursor. Okay, yeah, finally I got it. Okay, I don't know if you see the cursor while I'm moving it previously, but I get it at the end. All right, so this is the plot. Again, in the x-axis, it's the window size, with the width of the window or the search window, and the y-axis is the false accept rate. So if we have it 1, you can expect to have too many false positives. Imagine you're checking always single column. So you'll have zeros in almost all columns. All columns will have zeros, and when you search for 0, you'll find it, and then you'll figure out that the entire detection is just exact match. And that is wrong. When we go 2 bits, 3 bits, all the way to 4 bits, we start to have the minimum false accept rate. And when we exceed more, we start to lose some of we start to recognize more as false accept. Oh, sorry, as true accept. So all of them will be accepted, basically. Whether they are similar or dissimilar will be accepted. Why? Because we will have more zeros coming from everywhere. So the long zeros will start to dominate always. And since we overlap them and we greedily choose the zeros that maximize the segments that maximize the number of zeros, then we are going to always increase the number of zeros. So we see that 4 bits is the good number because think about this bit vector 101. It's 3 bit in length, and to detect the next segment, you should have a 0 either before or after. So remember that these segments are non-overlapping and next to each other. For example, this shape, or 1, 0, 1, and then the next segment will be full of zeros, right? And we might have a zeros over there. So that's why we need to overlap them as much as possible. For example, this one search window, the next search window will be over there. So within this region, we can know if there are ones or not. Although we overlap them, but we will never have 0 within this region, because from both search window, we will detect the 1 over there, which is starting of this segment of 0. So we will detect the 1 in both search window, and that will not be replaced by any of the overlapping search window. And that goes to have the 1 in the final Shouji bit vector. So again, maybe I can use different colors. I see some signs of clarity from some of you. Yeah, so let's use the green for this 0, 1, and then we have zeros over there. Now let's use different color for the red. Okay, so the search window will be 4. So it will span the 101 plus a 0 from there, right? Now the next search window will be, let me use different color. That is black. It will be over here. So in the red one, I will have 1010 as the largest number of zeros. Of course, that depends on whatever we have in the other rows or in the other diagonal, but basically this will be part of the correct solution. So mostly I will pick that one. In the black window, I will pick also 0100 because it has 3 zeros over there. Now, when I overlap the 2 sequences from here and from there, I will always get this one because it's part of the 2 solution. This is in most cases. Of course, some cases I might find other large zeros overlapping with these, and it might cause some problem later on, but that will be false positive, not false negative. the difference is false positive, it means they are dissimilar, but I'm saying they are similar to each other. And that's always fine, because as I said, we have the very last step, sequence alignment, to verify these sequences in a rigorous way or in an optimal way. So that's why we choose 4 bits. I hope it's clear why we choose it as 4, just to try to overlap the 2 segments of zeros together so that we make sure that there is a 1 between them to be correctly detected. Now, we try to implement it on FPGA. The good thing that we use counter of width 2 bits, each of these counters, because we're counting at most 4 bits. And to count 4 bits, you can, 3 bits, right? You need 3 bits to detect these 4 bits. However, the good thing, since you know the width of the bits that you're looking for, or the width of the search window, you don't need really to have a counter. What you need to do is enumerating all these possible values. So what are the values that you can have out of 4 bits? You can enumerate all of them. You will have about 16 options, right? And you can use lookup table to look up the values that you have. When you have the input diagonal, you can just check if it exists over there and store how many zeros in each of these values. For example, here, you know that you have 4, right? Here you have 3. Here you have 3 zeros, here 2 zeros, and so on. Here 3 zeros. So you can really store the number of zeros in each of these vectors to all of them, and then just look them up in the lookup table. You really don't need to count. What's the difference? If you use a counter, you need 4 D flip-flops that will operate in over 4 clock cycles. But if you want to use lookup table, that will be single clock cycle, and you can use single slice with a lookup table of 4 input at least, so that you can get it in 1 clock cycle. So you're doing saving with 3 clock cycles. And that is significant saving, especially if you are worrying about very long sequences, like 1 million long or 10 million long genomic sequences. So that is the nice thing about this design. We don't need to consider the full sequence. You can divide it into 4 at least, or exact 4 columns within each counter or lookup table, and then you can implement it using 4 input lookup table. So you really need to pick an FPGA that has this feature, which is 4 input lookup table. If you have 7 input lookup table, that's fine. You will not be using 3 of them. You'll use the other 4 input, but at least should be 4 input. If you have less than that, then you need to connect the lookup tables together so that you can solve one search window using multiple lookup tables. All right. So we do the counting concurrently for all of them using just single clock cycle, as I said. Now, the key results we got out of this is that up to 3 order magnitude faster than the C implementation. And Shouji Accelerate best performing CPU read aligner called EDLIP that was state of the art when we built this. And it's also 2.4x faster than GateKeeper and SSD, which is SIMD implementation or vectorized implementation of GateKeeper. All right, that was all for Shouji. Let me know if you have anything not clear. You can explain it again. The paper is available. The source code is also available. Feel free to edit it and build on top of it. Okay, so here's the second assignment for all of you. Don't worry, there's no due date. You take whatever time you want to solve it. It's very simple. Try to summarize the three things that we studied so far. So which one out of the 3 pre-alignment folders, GateKeeper, Magnet, and Shouji, is more efficient than the other? And why? So any insight, any hints? Anyone would like to answer it now? Okay, as a hint, I'm giving you this table. So feel free to fill up this table, and that will be the answer of the question. So you need to consider, for example, time complexity, space complexity, FPGA resource, accuracy, and speed. And all of them are reported in the paper. You don't need to worry about calculating them yourself. For example, the time complexity and space complexity of Magnet and Shouji are reported, both of them, in Shouji paper. You won't find it in Magnet paper, but please refer to Shouji paper in the supplementary material just to get which one is more efficient than the other. And we mention it over there clearly. The FPGA resource is also reported for all of them. The accuracy and the speed are reported over there. The justification, it's up to you, whatever you think or understand about it. As I said, in this homework, there is no due date. Feel free to submit it toward the end of the semester, for example, or whenever you feel free. And it will not be graded, but basically we would like to hear from you your thought about the justification. This is the purpose of the homework, but there will be no grade, even if you dismiss it. Okay? Sounds good? How many of you will take it? Yeah, feel free to speak up. It's okay if we are recording this. Don't feel shy. All right, yeah. So finally, to conclude, most speed up comes always from parallelism enabled by both novel architectures and algorithm. And as you see, we always propose first an algorithm, and then we try to find the suitable hardware architecture, a platform to be implementing, to implement the algorithm on it, basically. The options for hardware architecture is really wide. You can use GPUs, FPGAs, or even CPU implementation with SIMD support or vectorization support. You could also go with more recent architectures such as processing and memories from OpMem company or from Samsung. They start now providing memories with processing element inside it. So you can do the processing inside DRAM, for example, or you can use other recent technologies, for example, processing within the SSD itself. So all of these are options. There is no one best. Of course, each of them has their own advantages, disadvantages, and the use cases, when to use, when to not use, and so on. So we need to carefully tailor the algorithm for hardware and choose carefully the hardware for each algorithm. Again, all these are resources for you to study. And if you're interested in genomics or bioinformatics in general, you can check them out maybe after the semester finish. So you have more time to watch them. And yeah, we'll be always happy to have you again in the semester project, thesis project, master thesis, and so on, especially that all of you are doing your bachelor now. Some of you will be graduating soon. So we expect to have at least few of you joining us for thesis project. And this is the norm in all semesters. Normally we have 2 to 3 students contacting us after the semester, want to continue on the project that they are working on. All right, that was all from us. I hope it wasn't heavy load in the morning. Okay, I see some sad faces, some happy faces. I hope the sad ones will be happy soon.
Are you sure? Are you sure they are happy?
Yeah, I can see some faces happy, very happy, with wide smile. Yeah, as we said, there's no grades for these lectures. There is no exam and so on, just for your growth, your own benefits. I don't want to take more time, so enjoy the rest of the day and see you next week. Thank you so much. Bye-bye.